Well, okay, cool, thanks. So most of the, so I'm going to be talking first about some general problems in this area, and I'll go into one specific result. This is joint work with Salia, who have worked with Jeffrey and Judy, and my student Jose, and I haven't met Udianga, I believe, Salia's friend here. The general topic, we've been working on this for several years, and I acknowledge lots of collaborators and some of the recent work we've been doing with Judy's group. Okay, so, oh, okay. Too many. Okay. Okay, so just to give you a high-level idea of the problem, which is common to many network analytics applications, is finding a subgraph of interest. So we have a big graph G, and there is some small subgraph. So the first problem, the simplest problem, is I want to figure out whether the subgraph exists inside this. So is there an embedding which is isomorphic to this subgraph? And there are specific kinds of subgraphs which people look at: trees, paths, dense subgraphs, and so on. Or there are weighted versions. So each of these nodes have some weight, and I want to find an embedding which has the largest weight. There are other natural extensions. I want to count all these embeddings, or I want to find significant subgraphs whose frequency is different from a random graph with similar characteristics. So these are examples of common graph mining problems which arise in many different areas: social networks, public health, systems biology, and so on. Another problem which is also sort of related is to finding interesting subgraphs comes out of anomaly detection. And just to make it more concrete, I'll talk about one, I'll give you an example of one specific approach for anomaly detection, which is called network scan statistics. And this is based on the idea of hypothesis testing. So you have, so this is a weighted graph. So the graph, the nodes have weights coming from some process. The null hypothesis is that all the observations on V come from the same process. The alternative hypothesis for a cluster is that the observations are coming from some other process. So for instance, the null is they're all coming from Poisson with some rate. There's a cluster on which the observations are coming from some higher rate. So we want to find anomalous cluster. One can define in many ways. One example is the likelihood ratio. So find look at the probability that data came from this alternative hypothesis versus the data came from the null, and find a subgraph which maximizes it. So, and there are many different functions I'll show you in a minute. This was originally designed for spatial data. So people wanted to find spatial clusters, and now there's interest in looking at these problems in networks. So we want to find a connected subgraph which maximizes this. So this is related to this problem I said here. You want to find a subgraph which has some weight and some function on it, and you want to maximize that. So just to give an example of the kind of function. So this is one particular function called the Burke-Jones function. So don't worry about the details, but it has some expression like this. I just want to say it is nonlinear and pretty involved, and this is the kind of stuff that we have to deal with. The other thing which is recurring in many graph mining problems is the networks are dynamic. So in this example, I have the same network, but so the blue colors indicate weights which are changing over time. So the network might be fixed, the weights are changing over time, or the network itself might be changing over time, which makes the problem even harder. Okay, so let's skip this. So this is an example of many different kinds of scan statistics functions, which depend on what assumption you can make about the underlying data. So they're parametric, non-parametric, and there are lots of applications. So the point I just want to make from all of these is there are graph mining problems where you want to find some subgraph of interest with either just maximize, find whether a given subgraph exists, or some function you want to maximize. Those have a huge number of applications. And again, for concreteness, oops. So here is an abstract problem for this talk. So we have a graph, we have weights on the vertices. So we want to find, so the an example problem is there a path of size k which has weight at least b? Yeah, and extensions of this would be, is there a tree in this which has certain size and certain weight? So if we can solve problems of this kind, one can solve many of those anomaly detection problems that I mentioned before. Yeah, and feel free to interrupt if there are any questions. I don't necessarily have to do all the slides. Okay, so how hard are these problems? So these generalized subgraph isomorphism, so they are all NP hard. The counting versions are Sharpie hard. So don't worry about like those things other than you can't expect to have efficient polynomial time algorithms like worst case. The network scan statistics problems generalize Steiner connectivity, so those are hard as well. So one approach that we'll take in this talk, and it's gaining popularity, is this approach for dealing with NP-hard problems. So so what do you do if the problem has this kind of hardness? So one approach is called fixed parameter tractability. So we have input of size n, so the graph has n vertices. We want to have something which scales polynomially in the input size, but is exponential in some other parameter. So in the problems that we are talking about, the subgraph that we are trying to find, it has size k. So we want an algorithm, we are only looking for algorithms which are polynomial in n, but exponential in k. Yeah, right? So it is not exponential in n, so there is hope of at least doing something else. And of course, we need, I don't have to preach the choir here, we need parallel algorithms for both being able to store, spread the computation around, and so on. Okay, so what is known about these kinds of problems? There is some, okay, cool. Okay, so there's a lot of work on these graph mining problems, and I'll mention like at some very high level some of the techniques. So a lot of work is based on like bottom-up candidate generation. So you start building a set of candidates, prune, so you keep track of subgraphs of size 1, 2, and so on, and build candidates bottom-up. They have been adapted to pretty large networks for certain kinds of problems, but in general, they don't give rigorous guarantees on time, space. So, but they certainly have a lot of value. One of the techniques which has been used extensively is this really cool idea called color coding, developed long time back. It was first developed for counting paths. And here's a cartoon illustration of this. This is a really cool method, which if you look at the paper, it's fun to read. So we first pick a color for every node from 1 through k. So notice that the input has no colors. This is just an artifact of the algorithm. And then we are only going to count colorful embeddings. So in this example, we picked some coloring. And a colorful path is one in which the nodes have distinct colors. So this is a colorful path, but this is not a colorful path, right? So the colors here are distinct. So the good thing is, if you focus the problem on colorful embeddings, that can be computed by a dynamic program. So you can build up, and it's easy to keep far less information. So you can keep information of which scales with 2 to the k rather than k choose k. Rather than k factorial. That's the reason why this becomes fixed parameter tractable. So colorful embeddings one can calculate exactly using a dynamic program. And next, if you choose colors randomly, then the expected number of colorful embeddings is proportional to the actual count. And so there is hope of doing random coloring, and then counting the number of embeddings and getting the answer that you need. So this was the first fixed parameter tractable algorithm for this problem. Its runtime scales like 2e to the k, so some 4 point something raised to k times the number of edges, and the space is also 2 to the k times n. And this has been parallelized. So we had initial work using MapReduce, and then there was some work on using MPI, and we've been working with Judy's group using HARP. So I'll talk about a different technique. How much time is left? 7, 8 minutes? Okay. Sorry. Okay, cool. Yeah, so okay, maybe I'll rush through. We have been using a different, completely different algebraic approach for this problem, and I'll try to just give you a flavor of that technique and some results. So the idea is, so we're going to express, represent subgraphs as polynomials. So in this example here, there's a variable for each node, so x1, x2, and so on, and a subgraph v1, v2. This subgraph will express as a monomial, so xv1, xv2, xv4, and so on. And then we're going to sum up all of such subgraphs and look at those polynomials. So MVIJ is monomial, the polynomial which in which the monomials correspond to subgraphs containing node V, have size I, and weight J. Okay, so in this example, this subgraph and this subgraph have size 8. So M138 is subgraphs of size 3 of weight 8 containing 1. So it's x1, x2, x3 plus x1, x3, x4. Now, so far we've not done anything other than just change the represent them as polynomials. But the nice thing is these polynomials can be built bottom up. So you can imagine at an edge, first have a polynomial representing subgraphs containing U, subgraphs containing V. If you multiply them, things will work out. And if this, okay, so this, so you'll see things worked out. The only problem is if you start trying to do bottom up, you'll start getting squares. Yeah. So this is the supposed to be a polynomial which contains representing subgraphs which contain V of size 3, 8. So it has some right terms. So these correspond to actual subgraphs, but there are some square terms. And that's because we are building it like this. There's no other real way to do it. So the problem now becomes, you have a multivariate polynomial. Can you find, figure out whether it has non-square terms? Okay, so that's called the multilinear detection problem. And the cool trick, this again, this is all like from the theory literature. If you can evaluate it from an algebra which cancels out square terms, I'm going to skip all of this. Yeah, so basically the idea is we come up with a polynomial representation of the problem, plug in values for the variables from some suitable algebra. If the polynomial evaluates non-zero, that means it has the solution that we are looking for. Okay, so now this is our starting point actually. So we're looking at how to parallelize this. And we've tried both Giraffe, Spark, and MPI. So let me just okay. So let me just talk about some recent results trying to do this in MPI. And this is not considering any of the issues that you've all been talking about. Okay, so the algorithm that I have not gone through, it has this kind of structure. So there is some outer loop, 2 to the k iterations. For every node, we are trying to compute some polynomial and then adding them up and so on. So how do you parallelize this? So there are different ways you can easily think of. You can split the graph into processors and then try each of them try to do some iterations, or you can try to assign the whole graph to a processor, split this outer loop. We've tried those, and actually it turns out some thing in between works best. So split the graph across N1 processors, and they all run, take these iterations and split them evenly. So you'll have 2 to the k over N1 such outer iteration groups which get done. And we tried on some different graphs, and you'll notice these are much smaller than all the other kinds of things you would have seen. So there's some, I'll just take a couple of minutes. And so there's some interesting results when we vary this partition size. So as, the y-axis is the running time for this for paths. The x-axis is the partition size, so N1. As we increase N1, we see some interesting unimodal behavior. So the computation time goes down, the communication time goes up. There is some optimal value for the partition size. There is also other ways to, other interesting hooks for parallelizing, which I'm going to skip. Maybe I'll just compare with the color coding based approach. So one thing I I missed skipped in the slides is this approach brings down the space complexity from 2 to the k to k, and so k is the subgraph size. So the benefit of that is when we look at the MPI based method, that is not able to scale for very large subgraphs, but this algebraic method can handle much larger subgraphs. Okay, so that's scaling. I'm going to maybe just, okay, so I'm going to end. So basically, this subgraph detection kinds of problems are canonical in many different areas. And what I've talked about is bringing in algebraic methods for graph algorithms. I haven't talked about how we end up using this for anomaly detection. We're able to use adapt it for a broad class of scan statistics. The algebraic technique has lots of benefits. So space saving is huge, but there is still a lot of several limitations when you compare with color coding. First thing is I talked about the detection problem. One needs to do extra work if you want to find all the solutions, which is much easier in color coding. And then if you want to extend to more general subgraphs, that's we don't know how to do this with the algebraic method. That can be done easily with color coding. Okay, so I'll summarize by saying that there's a lot more room in the data analytics space. Things haven't been figured out yet, and yeah, hopefully there's some. You look at these questions into account when you're developing the systems and libraries. Thanks.